In this lecture of analog communication, we will understand the generation of DSB-SC modulated signal with the help of FET balanced modulator. DSB-SC modulated signal or double sideband suppressed carrier signal contains upper sideband signal and lower sideband signal. Here the carrier signal is suppressed and it is not transferred during the transmission of the modulated signal in order to save power and increase the efficiency compared to amplitude modulation. FET balanced modulator uses a field effect transistor such as JFET or MOSFET for the generation of the DSB-SC modulated signal. Let us look at the circuit diagram of the balanced modulator by using FET. The modulated signal is applied as an input to the primary of the input transformer T1 and the secondary of the transformer T1 is center tapped with the ratio 1:2. This center tapped secondary side of the transformer T1 generates two modulating signal having 180-degree phase shift from each other. So generated modulating signals are MT and -MT. The carrier signal is generated through the transformer T2. The generated carrier signal is applied to the center taps of the input transformer T1 and the output transformer T3 through the transformer T2. Here, FET used for the operation is MOSFET, which is a three-terminal device having gate, drain and source. The modulating signals generated by the secondary of the transformer T1 is applied at the inputs of the gate of the both MOSFETs and the modulated signals are in 180-degree out of phase from each other. Now the modulating signal and the carrier signal combine together as the voltage V1 or V1 is equal to CT minus MT and the voltage V2 which is equal to CT plus MT and applied as the input voltage between the gate and the source of the MOSFET F1 and F2. The output drain currents of the true MOSFET flows in the opposite direction and gets subtracted and works as an input for the transformer T3. Now the output drain currents in the carrier signal together produces the DSB-SC modulated signal as the output at the secondary of the transformer T3. Thus the DSB-SC signal is produced by FET balanced modulator. Before going any further, let's understand some basic points about MOSFET. A MOSFET is a three-terminal device having gate, drain and source. Generally, there are two types of MOSFET available, N-channel MOSFET and P-channel MOSFET depending on channel between drain and source. And a symbol of MOSFET looks like this, where gate, source and drain are termed as G, S and D. The structure of MOSFET looks like this. Every MOSFET has two heavily doped regions. For N-channel MOSFETs, two heavily doped N regions known as source and drain are grown on the P-type substrate or body, and the channel between source and drain for this type of MOSFET is N-type. For P-channel MOSFET, two heavily doped P regions known as source and drain are grown on N-type substrate and the channel between source and drain for this type of MOSFET is P-type. On the basis of presence of a channel between source and drain, MOSFETs are of mainly two types. Depletion type MOSFET, where the channel is already present in between source and drain. Enhancement type MOSFET, where the channel between source and drain needs to be created by applying a voltage between gate and source. Here we will use enhancement type N-MOSFET, which means that the type of channel created between the source and drain is of N-type and the minimum voltage required to create the channel between source and drain is known as threshold voltage or VT. Condition for creating a channel between source and drain: the voltage between gate and source of the MOSFET or VGS must be greater than or equal to the threshold voltage of the MOSFET or VT. After creating a channel between source and drain, if we apply a small voltage at the drain terminal with respect to source terminal, or if we apply VDS, then a current will start flowing from drain to source, and this current is known as drain current or ID. A MOSFET can operate in three regions depending on the applied voltage between source and drain or VDS, and these regions are classified as cutoff regions, triad region or non-saturation region, and saturation region. In the three different regions, the value of the drain current ID will be different. That's all for the basic of MOSFET. Now let's get back to the discussion of FET balanced modulator. The FET balanced modulator has two modes of operation. Mode 1, where the carrier signal is applied at the gate of the MOSFET, and the mode 2, where both carrier and the message signal are applied at the gate of the MOSFET. For mode 1, consider that there is the modulating signal or message signal is applied, then MT is equal to 0. The center step side of the transformer T1 with the ratio 1:2 does not generate any modulating signal. Input to the gate of the MOSFET will be the carrier signal, and this voltage is the gate to source voltage for the MOSFET 1, or we can write VGS1 is equal to CT. And similarly, input to the gate of the MOSFET will also be carrier signal, and this voltage is the gate to source voltage for the MOSFET 2, or VGS2 is equal to CT. And as there is voltage present between the gate and the source of the MOSFET, the two MOSFET will be in on condition. Then the current flowing through the MOSFET drain or drain currents of the MOSFET ID1 and ID2 will be produced due to the gate to source voltage and the biasing voltage VDD. The currents ID1 and ID2 are equal in magnitude but opposite in direction. Those two opposite and equal currents in the primary of the output transformer T3 cancels out each other. Due to this, input voltage to the primary of the output transformer T3 will be 0. Hence, no output is produced at the secondary of the output transformer T3. Thus, the carrier signal is suppressed. For the mode 2, consider the modulating signal is applied at the input of the transformer T1. This center tap secondary side of the transformer T1 with the ratio 1:2 will generate two modulating signals termed as MT and -MT. So, the modulating signals that will be applied to the gates of the two MOSFETs will be 180 degree out of phase. Input to the gate of the MOSFET will be carrier signal and the modulating signal, and as both carrier signal and the modulating signal are applied as input to the gate of the MOSFET, gate to source voltage for MOSFET M1 will be VGS1, which is equal to CT plus MT. Similarly, input voltage to the gate of the MOSFET 2 or VGS2 is equal to CT minus MT. Due to the voltage between gate and the source of the MOSFET will be in on condition. Then the MOSFET currents or drain currents ID1 and ID2 will be produced due to the gate to source voltages and the biasing voltage VDD. Since the applied modulating signals are 180 degree out of phase, the MOSFET currents due to the modulating signals are equal but not opposite. Hence, they do not cancel out each other. So the two drain currents ID1 and ID2 will not be equal in amplitude. Thus, the sum of two opposite drain currents and the carrier signal will work as an input to the primary of the transformer T3, and the DSB-SC output will be produced at the secondary of the output transformer T3. Let's see the mathematical analysis for two modes. For mathematical analysis, we will consider enhancement type N-type MOSFET, which is shown in the figure, and we will also consider the triode or non-saturation region of the MOSFET. Condition for this region of the MOSFET is gate to source voltage or VGS must be greater than the threshold voltage VT, and drain to source voltage or VDS must be less than the subtraction of gate to source voltage VGS and threshold voltage VT. For a MOSFET operating in the triode region, the drain current ID is equal to Kn prime W by L VGS minus VT minus half VDS into VDS, where Kn prime is equal to mu1 COX, which is the process transconductance parameter. Here, mu1 is the electron mobility and COX is the oxide capacitance of the MOSFET. At first, we will consider mode 1. For mode 1, only the carrier signal is applied at the gate of the MOSFET. So, message signal or modulating signal is equal to 0 and the carrier signal is equal to CT. Both MOSFET 1 and MOSFET 2 have the same carrier signal at their gates. So, gate to source voltage for the two MOSFETs or VGS1 equal to VGS2 will be equal to CT. And they will also have the same drain current. So, the drain current from MOSFET 1 or ID1 is equal to Kn prime W by L CT minus VT minus half into VDS into VDS, and the drain current from the MOSFET 2 is ID2 is equal to Kn prime W by L CT minus VT minus half VDS into VDS. Here both currents are same and are also equal in magnitude but in the opposite direction. Those two opposite and equal currents at the primary of the output transformer T3 will cancel out each other. So the net drain current or ID, which is equal to ID1 minus ID2, will be equal to 0. As the net drain current is 0, input voltage to the transformer T3 will also be equal to 0. Hence, no output is produced at the secondary of the transformer T3. So the carrier signal is suppressed. Minus. For mode 2, both carrier signal CT and message signal MT are applied as the inputs at the gate of the MOSFET. Hence, the gate to source voltage for MOSFET 1 or VGS1 is equal to CT plus MT, and the gate to source voltage for MOSFET 2 or VGS2 is equal to CT minus MT. So the drain current from the MOSFET 1 is equal to ID1 Kn prime W by L CT plus MT minus VT minus half VDS into VDS, which can be simplified as ID1 is equal to K n prime W by L MT into VDS plus K n prime W by L into CT minus VT minus half VDS into VDS. Again, the drain current for MOSFET 2 or ID2 is equal to K n prime W by L into CD minus MT minus VT half VDS into VDS, which can be simplified as ID2 is equal to minus K n prime W by L MT into VDS plus K n prime W by L CT minus VT minus half VDS into VDS. Here, the two drain currents ID1 and ID2 are divided into two parts. One part is due to the message signal and another part is due to the carrier signal. The drain currents due to the carrier signal are equal and opposite, so they will cancel out each other. Hence, the carrier signal is suppressed. Since the modulating signal is applied at the gates of the MOSFET M1 and M2 are out of phase by 180 degree, the currents due to the MOSFET signal are equal but not opposite in direction. Hence, they do not cancel out each other. So, the net drain current ID is equal to ID1 minus ID2, or ID is equal to 2 into K n prime W by L MT into VDS, which is applied as an input to the primary of the output transformer T3, and also the carrier signal is applied to the center taps of the output transformer T3 through the transformer T2. Therefore, the carrier signal and net current due to the modulating signal will work as an input to the output transformer T3 and will produce the DSB-SC modulating signal at the output of the secondary of the output transformer T3. Hence, the DSB-SC signal is produced by FET balanced modulator. That's all for this lecture. If you have any doubts regarding this lecture, then you may ask it in the comment section, and don't forget to hit the subscribe button, and see you in the next one.